Hey everyone, this video is about predicting the reaction direction and calculating equilibrium concentrations. In particular, we're using methane gas and dihydrogen sulfide reacting to produce CS2 and H2 gas. Now, in one experiment, 1 mole of the methane and 1 mole of H2S. Oh, actually, 2 moles of H2S. Let's correct that. One mole of CS2 and 2 moles of H2 are put together in a vessel. So it looks like none of this is not at equilibrium. In fact, it looks like a random amount of each of these almost, right? 1 mole of the methane, 1 mole of the CS2, 2 moles of H2S, and 2 moles of H2 have been added to a reaction vessel. And the question is, how is this equilibrium going to shift, left or right, to achieve the equilibrium constant of 0.036? Because that's sort of one of the points of this whole unit, right? That this equilibrium will either shift to the right or to the left to achieve this ratio of 0.036. So, first question we're going to ask and answer is, which direction will the reaction proceed to reach equilibrium? Is it going to go left or is it going to go right? And I guess the first thing we're going to calculate is not, in fact, K, but Q, right? We talked about this earlier in the videos. Q is the snapshot at any one given time. And so we're going to take a snapshot right when these things have been added at time 0. So let's do this calculation. Q is going to be equal to, when we write our species out, CS2 times H2 to the 4th power divided by CH4 times H2S squared. And let's plug in our concentrations here. It looks like all of these are in a 0.250 milliliter vessel, right? So we can't just plug in molarities, we need to plug in concentrations. So it looks like the CS2, or the CS2 here. So 0.250, right? 0.250, 1 divided by 0.250 is going to be 4 molar for the CS2. And with the H2S, right, 2 divided by 0.250 is going to be 8 molarity, right, molar to the 4th power, divided by methane's concentration of 1 divided by 0.250, which will be another 4, and H2S's concentration, 2 divided by 0.250, which is 8. And in this scenario, well, this could be easy. The 4 divided by 4 will cancel. And then we could see how these exponents change, right? So if this was a 4 up here and this is a 2, 8, this is 8 times 10 to the second. So that simplifies to 64.0. You don't even need a calculator. So now we know that Q is equal to 64.0. Whoops. 64.0. Now that is actually quite a bit greater than K, which is equal to 0.036. So what this means is, if this ratio Q is greater than K, that our our reaction right now needs to shift to the left. So it shifts to the left to lower this ratio, to lower the concentrations on top and increase the concentrations on bottom, to lower the product concentrations and increase the reactant concentrations. So this reaction shifts to the left to achieve equilibrium, consuming some of the products and actually increasing the concentrations of the reactants. Part B asks a different question. If methane's concentration is 5.56 molar at equilibrium, what are the equilibrium concentrations of the other substances? Well, here a rice table would in fact be useful, right? Because we're talking about having an initial set of conditions and then changing them. Why don't we switch to blue? So our reaction, right, CH4 plus 2 H2S CS2 plus 4 H2. And what we found out before was that this initial concentration was 4 molar. This was 8 molar. This was 4 molar. And this was 8 molar. And, you know, even though, well, we don't know technically. I mean, I guess in this scenario, we did know which direction the equilibrium would shift, right? But when we're doing this change, to some degree, the system will correct itself whether we do plus or minus here, as long as we're consistent. So we're going to say that right here, because we're shifting to the left, right? We're shifting to the left, that this side is going to get bigger, and this side is going to get, and the products side is going to get smaller. So we're, instead of subtracting on the left, we're going to add it to the left. So this is going to get bigger by x. This is going to get bigger by 2x, right? Because this is a 2 here. This is going to decrease by x, and this is going to decrease by 4x. So at equilibrium, our methane's concentration is 4.00 plus x. Our H2S concentration is 8.00 plus 2x. The CS2 concentration at equilibrium is 4.00 minus x. And the H2 concentration is 8.00 minus 4x. Now the concentration that we do know at equilibrium, right? The methane at equilibrium, I'll put a sub EQ, we're told is 5.56 molar. And then this scenario here we can plug in. We know that that's equal to 4 plus x. So from this we can determine that x is 1.56 molar. So if x is 1.56 molar, the H2S concentration at equilibrium is 8 plus 2x. So it's 8 plus 2 times 1.56, giving us 11.12 molar. The CS2 concentration is equal to 4 minus x. Well, whoops. We'll plug in what that x is here. 1.56, and that is 2.44 molar. And we have the H2 concentration, and that's equal to 8 minus 4 times 1.56. And that's equal to 1.76 molar. So by using a rice table, we can envision how these different concentrations change. And of course, by knowing what the methane's concentration is, we can deduce what the rest is by solving for x. So that there is how you determine whether or not, part A, a reaction will shift to the left or right. You compare Q to K, and as we said in an earlier video, if Q is less than K, the equilibrium shifts to the right in order to increase the products and decrease the reactant ratio to approach K. If Q is greater than K, as we were in this case, the reaction shifts to the left to lower that ratio by increasing the reactant concentrations and decreasing the products. And of course, if Q is equal to K, then we are actually sitting at equilibrium.